Okay, so before we talk about the optimizers for training deep learning models, we can have an appetizer or the toy example here first for you. It is about the training process or the optimization process of a very simple function, about the quadratic function. So let's assume we have a very simple function, which is quadratic. I mean, this function, this y equals to x squared minus x minus 2. This function is so easy, and we have learned this function before, right, in our high school, I think. And then the question we are starting here is how can we achieve the minimum of this function at which x? In other words, we have to decide the lowest point of this function curve and also decide this x value which can achieve the minimum, right? If we draw this function, we choose with some tools, we can show the curve of this function on the right hand side. Because this function is quadratic, we know this function will have one single minimum, right? And it can be obtained with one single point above the minimum. So according to the quadratic function, this curve, we find that this function can achieve the minimum at what? At x equals to 1/2, right? At this point. And as to the function value, when x equals to 1/2, the function value will be equals to negative 9/4, right? So this is based on our prior knowledge. And how can we achieve this minimum based on our prior knowledge? If you still remember when we are learning or starting the algebra, this course in math, we can obtain the minimum value for this function with a method, right? We can calculate the partial derivative of this function with regard to the variable, right? In other words, we can calculate the partial derivative of this y with regards to x. Because this function is so simple, if we calculate the partial derivative of this function to x, it will equals to what? It's x squared, the partial derivative to x will be equals to 2x, right? For this negative x, its partial derivative to x will be equal to negative 1, right? As to the partial derivative of this constant to x, it will be equal to 0, right? So by calculating this partial derivative of this y with regards to x, we can obtain its result to be 2x minus 1, right? It should be very straightforward for you based on the algebra courses we have learned before in math. Then by making its partial derivative, equal to 0, we can obtain the x which can achieve the minimum for this function, right? So by making this term equal to 0, we can obtain x will be equal to 1/2, right? It will be equal to 1/2. So by making this term equal to 0, in other words, we want to find a point at which point the function curve will have a 0 gradient, right? In other words, at this point, the function is not decreasing, it's not increasing. So at this point, its increasing trend will be flat, right? How can we achieve this point? So we know for this function curve, for the points at the left-hand side of this blue dot, it will be all negative, right? Because this function is decreasing on the left-hand side. However, for the points on the right-hand side, it will be increasing, right? In other words, this trend will be a positive value, or the gradient will be a positive value. Only at this point, its gradient will be flat, it will be 0, right? Because for this point, if we draw a line which incident to this point, it will be a flat line, right? Its gradient will be 0. Then in this way, we can find the data point introducing the 0 gradient, which will be equal to 1/2. And by replacing this x equals to 1/2 into this function, we can obtain the minimum value for this function to be negative 9/4, right? So this is the way we do the optimization with our algebra knowledge before. And in this way, we can obtain the precise minimum value for the function as well as the specific x value, which can introduce this minimum value for the function. So this method actually is very straightforward, I think, for you, right? And we can also obtain the precise minimum value in scenery. And however, it also has some shortcomings because this method only works for some simple functions, like for a quadratic function, because this one is convex. So for some of the function shapes, they are convex. In other words, we can find one single or minimal value for this function. And also this function only has one single variable, this x, right? And it cannot work for more complicated cases, like for non-convex functions or with multiple variables to be learned. So, for example, when we are training the different models, we have to design our model architecture as well as the loss function. In many of the cases, the loss function will be non-convex. Also, for the different models we are training, we have so many variables to be learned. So then this kind of method cannot work well for our deep learning training anymore, right? And then you may wonder, do we have any other method for solving this kind of problem or not, and to achieve the minimum value for this function? The answer is yes. We can also have some other methods. The method we plan to introduce next is called gradient descent. The gradient descent is also based on the partial derivative of this function regarding to the variables. However, we are considering this gradient for the function at many points. So for the gradient descent based method, we are doing the optimization by searching for the value or the variable values which can introduce in the minimum value for the function iteratively. So let's assume we are still starting this function, the same function, the quadratic function we show here, right? We also draw the curve on the right hand side. So we know it can achieve the minimum for the x equals to 1/2, right? And for all the points on the left hand side of this x equals to 1/2, its gradient will be negative, right? Because we calculated the partial derivative of this function towards x to be 2x minus 1, right? We'll draw this function, for the gradient function curve on the bottom of this page. It will be equal to 2x minus 1, right? So for all the points on the left hand side of 1/2, for x 1 equals to 1/2, it will be all be negative on the left hand side, right? And for all the points on the right hand side for this gradient function curve, it will be positive instead, right? It can achieve the zero gradient for the x equals to 1/2. Okay, then let's have a look at how this gradient descent algorithm works. So the gradient descent do the searching for the minimum of this function iteratively, starting from some initial points. Let's assume we are doing the searching starting from a random point x0. This is the random pick point for the function in the range of variable values. We can randomly pick one single point x0 and starting the searching from this point. And the gradient descent do the optimization with the iterative process. In other words, we are updating this variable iteratively. And how do we do updating? We calculate the partial derivative of this function regarding to the variable at each of the points we are doing the searching. For example, if we do the random initialization x0, and then we can calculate its current gradient to be partial derivative of this y to x for this x0, right? And we can calculate its current gradient for the current variable values, like x0, for example. And then we can denote this gradient to be gi because we are doing the iterative updating. This I denotes the iteration number. The I is iteration, right? And we can denote this gi to be the derivative of this function regarding to the variable at each of the points. Then, based on the gradient as well its current variable value, like x0, right? And then we can further update this x to be a new value. And the updating equation is denoted by xi plus 1 equals to xi minus alpha times gi. This is xi denoting the current variable value, right? And this gi denoting its current gradient. And this alpha is the learning rate. Normally it is a positive number. It's a very small number, denoting how many steps we will go forward. And here we have xi minus. This minus is important. We're doing the minus of the gradient. And then we can do this process iteratively until convergence. What do we mean by until convergence? If we can achieve this xi and xi plus 1, they have very minor difference, then we can say this updating process will converge, right? And we will stop this updating process until converge. And finally, we can achieve this x at convergence, denoting it as xn, right? And we can replace this xn into this function to calculate its corresponding minimum value for the function. Okay, so this is this gradient descent algorithm, and then let's have a look at what does this learning process mean, or the updating process mean. And let's assume we do the initialization of this x0 denoting this point, right? We're doing the searching from a random point x0. Then based on the function partial derivative function, and we can calculate its current gradient, right? Because we know this x0 is on the left-hand side of this x equals 1/2. Its a gradient on the left-hand side will all be negative, right? We know it is negative gradient. And then if we're replacing this x0 as well as a negative gradient into this equation, this xi minus a negative gradient will do what? It will further increase its x value, right? Because we know its gradient is negative here, in other words, we have to further increase its x to move this x to the right hand side slightly, and we can achieve lower y value for this function, right? So by increasing the x slightly, we can achieve a small number value for this function. In this way, we can do the stepwise updating and according to the gradient. Alright. So then we can move to the next point here. Its gradient is still negative, right? Then we can move to this point instead, and to this point, right? Let's assume until we're reaching one new point like this one. And according to this location regarding to, its gradient, we know its current gradient is still a negative gradient. Let's assume so, right? And then according to this equation, we have to further move this point to the right hand side slightly. Let's assume we move this point to this point instead, right? According to the curve shape, we know this we moved slightly overhead actually, and we have to move back. The way we do the moving back is according to this equation as well, because according to the equation of this new point, we know its current gradient will be a positive number, right? According to this equation, we have to minus this alpha times the current gradient, because the current gradient at this point will be a positive number. In other words, we have to decrease its variable value instead, right? Slightly. And for example, we can move back to this point, which will achieve the minimum value for this function, right? So according to this equation, it allows us to adjust the position or the location of the certain point starting from the initialization, right, until convergence. If this function has some minimal points, then iteratively we will achieve, or we will approach this minimal point gradually via this iterative updating, right? And then you may also wonder how far or how fast we can move this point. The speed we are achieving this convergence actually depends on two factors. The first one is for the gradient. If this gradient has a very large value, or it has a very large absolute value, then we can decrease this x in a faster way, right? Because we are minus a large number here, right? It also depends on the learning rate. It's alpha. Alpha denoting a number, or normally it is a constant. It denoting how fast we do the updating actually. We have to assign alpha with a very small number. Later on, we will have one page for how to assign alpha and how it will affect the learning process. I hope you can understand me right now. We do the iterative updating of this function regarding to the variable. And it depends on the location of the current point, and it will calculate the gradient and further utilize this gradient to help us updating these variable values until we can achieve the convergence. Okay, so this is another way we will do the optimization of this simple function based on the gradient descent. In the following pages, for the deep learning model, these algorithms, we will train them all based on the gradient descent algorithm actually. In other words, we have to do this iterative updating of this function regarding to the variables. This is a very simple case, and in the following pages, we have more complete cases to show you and how this algorithm will work.